In this episode, we take a step toward hypothesis testing by examining the one-sample z-test. This is Totally Doable Stats. Hey, so last episode we looked at z-scores, which is also a first look at score standardization. It's a valuable calculation to learn, but what if someone wants to compare an entire group of scores? Then the z-score falls short, but we can turn then to the z-test. To do this test, there's an important transition we need to make. Up to this point, we have been working with distributions of scores, but when we start comparing a group to a population, we transition to working within a distribution of means. The benefit to working in a distribution of means is that when a group of scores may not be normally distributed, a group of means of those scores likely will be. The difference really falls into the measure of spread. When we're working with a group of scores, spread is measured by the standard deviation. However, in a distribution of means, we measure spread using the standard error of the mean, or simply standard error. We do this because we want to make sure we account for any possible error we have in our sample means estimate of the population mean. And we calculate it by dividing the population standard deviation by the square root of the number of items in our sample. And we'll denote this using sigma sub m. For mu sub m, our mean of the means, we'll use just mu. And so our formula, again, sigma sub m equals sigma over the square root of n. And so for our z-test, instead of x minus m over sigma, the z-test will be m minus mu sub m over sigma sub m, where mu of m equals mu, and sigma sub m equals sigma over the square root of n. So it seems to me the easiest way to move forward would be to work out an example. So let's take a look at this. Each year, thousands of hopeful future doctors have to take the Medical College Admission Test, or the MCAT, as part of the application process to med school. And each year, many of those test takers fail to reach an acceptable score. Suppose a company creates a new study method for improving MCAT scores. This company randomly sampled 37 students and found that after completing their 6-week test prep protocol, these students averaged 517 on the MCAT. Given that over the past 3 years, the national average is 500.9, standard deviation of 10.6, did the protocol allow students to gain significant improvement? This is a great measure to go through and figure out how the z-test works, because the z-test essentially functions as a one-sample z-test. It's a way to compare a sample to a population at large. And we have all that information here. And so as a reminder, our formula is z equals m minus mu sub m, because we're working within a distribution of means, over sigma sub m. From this example, we have our mean for our test takers was 517. And how many of them were there? There were n equals 37 students who took the test. We also have the information about the population. So mu, which we're also going to use as mu sub m, equals 500.9, and standard deviation, or sigma, equals 10.6. So for the numerator in our z-test, well, that's pretty straightforward, right? We've got 517 minus 500.9. But for our denominator, we actually have to go through an extra step to figure that out. Sigma sub m, or our standard error of the mean, is going to be the standard deviation of the population divided by the square root of n, which in this case equals 10.6 divided by the square root of 37. So as I check my calculator, if I take the square root of 37, that's going to be 6.08. And so if I then take 10.6 divided by 6.08, I find a standard error of the mean of about 1.74 for my standard error of the mean. Which means when I put that over here in the denominator, I'm going to end up with 16.1 over 1.74, which equals, let's see, 16.1 divided by 1.74. I end up with a z-test result of 9.25. And that's really it. When I go through and I calculate this result, it gives me the answer for my one sample z-test that I can then take from there and make a meaningful comparison to determine if I've made a statistically significant difference. And so between this and where we're going to head in the next couple of videos, thinking our way through how to really do hypothesis testing, what differences I can think through in terms of one-tailed versus two-tailed tests, those kinds of things. We're going to be putting all of that information together to really get an understanding of how these statistics begin to work. Now we're actually starting to get into the statistics that allow us to do hypothesis testing. And my hope is that even though things are getting a little more complicated, you can see that these are still totally doable stats.